Pac Droids has been called one of the most innovative Pac-style games for any platform. It's like if Pac-Man not only ate dots and power pellets, but could shoot the ghosts. And the ghosts can leave mines behind. But to me, the most innovative thing happened before you even started to play. When you load a program from tape onto the CoCo, you run the cload or cloadm command. Wait for it to load into memory, and then you execute it. But Pac Droids was different. You run cloadm, but then it somehow manages to take over the machine while it's loading, and then eventually runs itself. And then there's... If there were any rules about how a program was supposed to behave, Superkid broke them all. Everything from speeding up the pitch of the cassette audio, to encrypting its own machine code, to executing other code that isn't even code, to rewriting its instructions after it executes them to cover up its tracks, to hiding taunting messages for us as we try to learn how it works. Today we explore how programs are stored on cassette for the CoCo and Dragon computers, and reverse engineer the ingenious hacks that some 80s developers used to commandeer the loading process. Pac Droids was the first game I remember seeing that took over your machine as it was loading. If you wanted to make a backup copy of a game, typically you would just load it, and then when it was done, save it back out on another tape or disc. But if the basic interpreter itself gets hijacked, you lose control of your machine. Pac Droids does this by a creative use of the tape format. The CoCo stores programs and data on tape using specially formatted blocks. A typical program starts with the file header block, 8 bytes for the file name, 1 byte to identify if this is a basic or machine language program, a couple bytes related to ASCII and crunching, which we can ignore for now, a 2-byte address of where the exec command should start executing the program, and a 2-byte address of where in memory to load the program. Next, a series of data blocks, each with 255 or fewer bytes. This is the actual content of the program. Finally, an end-of-file block. The first strange thing that Pac Droids does is to specify this address for where it wants to be loaded. 010C is the IRQ vector. The CoCo has a timer that goes off 60 times a second. This is called the field sync interrupt. When this timer goes off, regardless of what the CPU happened to be doing, it gets rudely interrupted. Its state gets saved so it can resume what it was doing later, and then it jumps to the interrupt service routine. This is special code that gets called whenever the timer goes off, to do useful tasks separate from the mainline code of a running program or the basic interpreter loop. The interrupt service routine typically does short tasks to aid with video display and music. And this is Pac Droid's way in. The tape's file header block for Pac Droid uses 010C as the load address. This is a special location in memory called the interrupt vector that only has 3 bytes reserved. Normally, the 3 bytes are simply an instruction to jump to the real interrupt service routine. But that's not what Pac Droid does. Pac Droid starts loading itself here and doesn't stop at 3 bytes. It loads over 100 bytes, destroying everything in its path, including all sorts of internal bookkeeping used by the basic interpreter. That might seem rude and dangerous, but Pac Droids, like many games, did not expect to return back to the basic interpreter. It was effectively the new operating system for your machine. If you wanted to go back to basic, you had to reboot. The important part is that Pac Droid's code starts loading at the interrupt vector, which means that the next time the timer goes off, this is the code that will get run. A typical interrupt service routine does its work quickly, and then returns so that the CPU can resume whatever it was doing when it got interrupted. But once Pac Droid gets control, it will not let go. But Pac Droids has more tricks up its sleeve. That code that's loaded at the interrupt vector isn't even the game. It's a custom loader, and it's used to load the rest of the bytes that are the actual game. So far, cloadm has loaded the file header block, a block containing the code for the loader, and an end-of-file block. Normally, the next thing on the tape would be a new file, and thus a new file header block. But that's not what Pac Droid does. Instead, Next is a series of 255-byte long data blocks without a file header to introduce them, and without an end-of-file block after them. This is part of what confuses so many backup programs. Once they see the end-of-file block, they think they're done and completely ignore the data blocks which contain the actual game code. But even if they did continue to read the next block, they'd get confused because there was no header. They wouldn't know where to load that data to, or that it even belonged to Pac Droids at all. But since Pac Droids' custom loader is what's running now, it knows exactly what to do with those data blocks. It loads them starting at address hex 600, but not before it changes the video display mode and tells the video chip that screen memory shall now start at hex 600. That means that the game data doesn't actually start with code, it starts with the splash screen pixels, and they're loaded directly into the screen buffer to be displayed to the user. Immediately after the splash screen pixels, the actual game code begins. The loader simply keeps on loading until it detects enough bytes have been read. Then it jumps straight into the game code. What's crazy is we're still in the interrupt service routine. In fact, the entire game is technically one incredibly long interrupt service routine that never exits. But it works, so whatever. If you know something about interrupts, you're probably wondering if this approach is vulnerable to crashing. What if, while cloadm is loading the Pac Droids loader into the interrupt vector, the timer happens to go off? Would it be possible that we would start to execute some combination of the new bytes we're loading into the interrupt vector and the old bytes that were there before? Well, unlike the floppy drive, when loading from tape, the basic interpreter disables all interrupts. So that timer is halted as long as cloadm is doing its thing. Once the Pac Droids loader has been fully loaded, cloadm thinks its job is done, and it re-enables the interrupt. That's when the Pac Droids loader gets control to start loading the actual game. There's one footnote to this Pac Droids section about some extra copy protection that bit me while I was working on this video. I had written some code to regenerate the data blocks from an emulator, so I could have a crystal clean recording for the Color Computer archive, as opposed to my original backup that I had created 40 years ago. That's actually supposed to be silenced before the data blocks begin. And there they go. That's really dirty and could not be read back into my CoCo, although somehow MAME was able to read them. So I wanted to use MAME to regenerate the data blocks so that it could be archived for anyone. When I was done regenerating the data blocks, I tested them by reading them back in. It looked like everything was working fine. But then I noticed that the splash screen seemed to be missing some lines, and then it just hung the computer with no way to play the game. What I didn't realize was that between the end-of-file block after the Pac Droids loader and all the data blocks of the actual game code, the length of the silence mattered. The Pac Droids loader actually counts down from about 327,000, allowing the tape to continue playing before it would start listening for the data blocks. So if the silence on the tape wasn't long enough, the loader would miss the earlier bytes, throwing everything completely off. I had to regenerate the data blocks, but with enough silence before them so that nothing would be skipped. If you're curious how I managed to make a backup of the game all those years ago, I was able to defeat all of these issues with a simple, blunt approach. Have you ever made a mixtape? Yeah. You couldn't do this for many generations before the result became unusable, but it worked once. Pac Droids was sneaky, but it is nothing compared to what you're about to see with Superkid. I'm about to show the actual loading of the Superkid game, but be warned, there is a lot of flashing involved, so if you're sensitive to flashing, you're not going to want to watch that. I will put a countdown on the screen to give you warning, then you'll want to look away, and then I'll let you know when it's safe to look back. Like Pac Droids, you see cloadm and it'll start loading. You're going to have about 5 seconds before the flashing starts, so be prepared to look away if this is bad for you. For those of you who are watching, you'll see that in addition to the flashing, we have something coming in onto the screen in stripes. And we're going to talk a little bit later about why the flashing is happening and how this stripe thing is happening. As we'll see later, I believe this flashing is completely intentional. My guess is that many people would look at it and say, oh, that's not horrendous. That is getting me really energized to play this very cool game that is causing all sorts of trauma to my TV. Alright, if you looked away, it's safe to look back at the screen. Here we have our splash screen. There are only 4 colors allowed on this screen, so the artist did a nice job of mixing and matching colors to get more apparent colors out of this. You'll notice at the top that the load time is about 3 minutes, so we're just going to skip ahead to the end. Synthesized voice. And here you see it started automatically, and it's playing some nice multi-part music. In fact, we're going to skip ahead so you can hear some of the different tunes it plays. And notice how the Superkid character kind of moves in time with the music. So already we're seeing a lot of innovations, multi-part music, synthesized voice, advanced graphics, and if we start the game,
Go get him, Superkid.
You'll see we have parallax scrolling, all of this on a machine that doesn't have dedicated sprites or a dedicated sound card. The programmer clearly had really good technical chops, so you can only imagine what efforts were put in to do copy protection. Did that sound like a British accent? To understand the first weird thing that they do, we're going to take a look at the actual waveform of the audio that was stored on the cassette. Here you can see the file header block. These are the data blocks just for the loader. And here, until the very end, are all of the data blocks for the game itself. Now we're going to listen to the pitch of how this starts. If you look here, you're going to see the file header block is going to start at an F sharp. Now that the loader is loaded, let's take a look at the pitch of the rest of the data blocks for the whole game. It starts on a G. So the Superkid loader was stored normally, but once it's run, it is expecting the rest of the data blocks to be stored at this higher pitch. Much like Pac Droids, when we run cloadm, we end up loading the Superkid loader. Once the Superkid loader is loaded, cloadm thinks it's done and has no idea that the actual data bytes for the game come later. I've disassembled and commented the Superkid loader so we can take a look at what this code is doing. The first thing to note is that it loads very early in RAM. It doesn't load over the IRQ vector, but it does load in the middle of the basic working storage area. And it starts with a whole bunch of garbage. This code does not do anything. But there are a few interesting jump instructions. Jump to 1F4. Jump to 1F4. Jump to 1F4. These jumps are being written into that area of basic working storage known as RAM vectors. RAM vectors are hooks that earlier versions of BASIC can use to allow later versions of BASIC to intercept calls. This allows, for example, disk extended color BASIC to extend a routine that was originally written in the very first color BASIC. Each of these RAM vectors only has 3 bytes reserved, which are either a return if nothing is hooking them, or a jump statement to the destination of the hook. So it would look like Superkid's loader is intentionally overwriting many of these RAM vectors with a jump instruction. And where exactly is 1F4 jumping to? The very beginning of the actual loader code. So this is the code responsible for taking those later data blocks that were recorded at a pitch that was a bit too high and reading all of them in and then executing the code once they're read. We'll return back to this code to see exactly how it's working, but just to give you an overview, I'm just scrolling through it so you can see, and you'll notice that in addition to code, the programmer left a few taunting comments. The word stage appears in the game, but after that is some stuff that only exists for prying eyes. Nosy bugger, copyright 1987, Wayne J. Smithson, warning. Anyone found with a pirated copy of Superkid will be beaten up by friends. No joke. Well, I can't hang around like a fart in a phone box. Bye. So let's take a look at how the Superkid loader actually gets control. It does something very different from Pac Droids. We're looking here at the source from the Dragon ROM. We're actually going through the Dragon version of Superkid for this video. And we're looking at the code that would execute once cloadm is complete. So cloadm has finished loading the loader and it thinks it's about to execute the next basic command, but it has a surprise in store for it. When a command is finished, you should either have a colon indicating a new command is on its way on that same line, or the line itself should be finished. We end up here because we're not at the end of a line. There's actually another bit of text after the cloadm command. But that, in fact, is a lie. Here we are in the MAME debugger at that instruction where we're comparing A with the colon. A was grabbed from this location of basic working storage, which would normally contain the command that the basic interpreter is executing. If we take a look at that area of memory, perhaps this will look a little familiar to you. Here is that taunting message that we were given. And here is where BASIC believes is the next character of that command. The hex value 42, which is now in the A register. That corresponds to the capital letter B in bugger. That's not a colon. So that's going to cause the basic interpreter to throw an error. That's going to send us off here to the error handler at 89B4. Another jump later, and we end up jumping to the error handler RAM vector. Yes, that's right. When an error is thrown, we call a RAM vector to see if a later version of BASIC wanted to hook that error. I wonder what's at this RAM vector. Oh, it's a jump instruction to the very beginning of the loader. It's interesting that so many of these RAM vectors have that jump to the beginning of the loader. It's as if they weren't sure which one would be hit, so to hedge their bets, they just sprinkled it everywhere. And the one that stuck happened to be the error handler. So cloadm is finished, it returned to the basic interpreter threw an error, and that is what causes us to finally start executing the Superkid loader. And now the Superkid loader is in control. The first thing it does is it sets up the reset vector. If anyone were to try to hit the reset button on the computer, this would ensure that we end right back up at the loader. We also changed the stack pointer to a very small number very early in memory. This is not normal. The stack pointer usually starts at something very late in memory and then works its way earlier and earlier. Here it's starting very early in memory. In fact, right at the point just before the loader code itself. We'll find out why later. The next thing we do is we take all of those jumps that were added to the RAM vectors and remove them. So you can see here's a jump to 1F4, 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 1F4. And as we step through this code, they all just get replaced with RTSs. It's like it's covering up its tracks so that if anyone were to look at memory after the loader had started executing, they would have never seen the evidence of how it got the loader to execute in the first place. The next thing is important. We're taking this value that's stored in basic working storage that was a hex 12, and we're turning it into hex 11. This is a parameter to the cassette loading code, which describes the minimum cycle width. When the basic ROM reads the pulse from the cassette, this is kind of the magic threshold that determines whether we're reading a 0 or a 1. By making this a little shorter, you allow the cycle width to be a little bit shorter, which I think is what explains why the frequency goes higher, why the pitch seems to go higher for these blocks that the loader reads versus the normal blocks that the ROM normally reads. The loader is actually using many of the cassette reading routines in the ROM, but by changing this constant, it changes how they respond to the actual audio that they're reading. Next, we clear the screen. We change the video mode to the graphics screen. We manually turn on the cassette motor. We read in one block. This is a special block we're going to come back to later. From this point forward, we're no longer going to read block by block. Instead, this code uses lower level routines in the ROM to just read bytes. We're starting with the splash screen through these addresses, but we're doing a couple strange things. Each byte we read into one memory location, but then we increment our pointer by 2. The striping we were seeing before is because we start by loading the bytes only into even memory addresses, then the next series of bytes are read only into the odd memory addresses. And the flashing is happening because of this code right here. We read the value of the display mode, and we exclusive OR this value, which ends up toggling bits 3 and 4. The important bit there is 3, which is the color set. So we keep swapping the color set between 0 and 1, 0 and 1 on every single byte that we read, causing that horrendous flashing. We're going to watch this again, but I'm going to turn off the flashing by just getting rid of that store instruction. If I change that to just a load instruction, it will effectively do nothing. And then we can have a clearer view of how the splash screen gets loaded. So we'll overwrite this store with a load, and this store with a load. And now we'll let it continue. And we can see we got those stripes coming in, and then we got those stripes coming in, and now we're ready to load the rest of the game. The rest of this code reads in the bytes of the game, and it flashes a cursor like a bit of a progress indicator to show that the loading is still happening. It does that by taking the bytes from here through here in video memory and inverting all the bits. For every byte we read out of the cassette, not only do we store that byte into memory, checking for the end condition, but inverting the bits of whichever line of that cursor we happen to be on, advancing our pointer to the next line of that cursor to invert next time around. Once we reach the bottom of the cursor, that tells us it's time to branch back up and start back up at the top of the cursor again. When we're done loading everything, we finally end up here. The next bit of code takes those letters from the word stage and writes them into basic working storage over a few of the variables. And then we return. But we return to where? Well, that depends whatever's stored at the stack pointer that's currently in S. And remember, we initialized S with a very early memory location, 1E8. And it turns out the loader ensured that 1E8 would have us return to 8000. This is where we go on a boot. So this sends us to a ROM routine to initialize the hardware, which is this code here, and which ends at an odd instruction. This will jump us to whatever address happens to be stored in the Y register by the time we're done with all of this. And the Y register has been carefully ensured to be 0. Well, now that can't be right. Let's see. And oh my gosh, we're off-roading. We're executing memory that isn't even code. This is not a road, this is dirt. We are executing through dirt that shouldn't even exist. What is happening? It's kind of a miracle that we can even pass through this without jumping elsewhere or crashing. But we're going to go all the way until we get to address A8. That jumps us back into the ROM. But now the stack address is 1EA, and when we return based on where that's pointing, we end up at 3B0, back into early memory, but this time at actual code. In fact, this is the very code that is the first block that's read by the Superkid loader. I told you we'd be looking at this code later, and now is the time. This code decrypts all of the code that we had loaded in for the game. We're actually going to take a look at the code that was loaded, and we're going to see it is utter garbage. This will rewrite that code by decrypting it into actual instructions. Yet another copy protection scheme added to this incredibly complex layer of onion-peeled copy protection madness. The decryption scheme is very simple. We read 2 bytes, and we swap them, and we write them back. But just in case that wasn't enough, first we're going to rewrite this instruction that was a load X into a compare X. This is the boundary condition of our loop. It makes no sense to be a load X. It needs to compare X with this value to tell us whether we're done decrypting. So we execute a few instructions, and boom, now that's a compare X. I don't know why this one extra little bit of nonsense was useful, but holy cannoli. So now we're going to start swapping our bytes, and it's not going to make much of a difference. Not until we get down to some actual code. And if you look at the left, you'll see the code is now starting to transform into its final form. We're starting at 3400, which is where the game starts executing. But it is possible the disassembler is getting confused in case there might be data mixed in with the code. Once we've finished transforming all the bytes, we're sitting at yet another enigmatic return instruction. Where are we returning to now? As usual, our stack pointer is pointing somewhere very early in memory, and all the machinations until now have ensured that that will point us to 3400. And now the game can begin. I plan to upload the auto-executing version of Pac Droids on the Color Computer Archive, so check the description. I'll put a link there when it's up there. I'll also put a link in the description to Superkid. Thanks to Kieran for preserving and uploading that. And also thanks to the folks on the CoCo Discord and the CoCo Nation. Very often conversations up there will inspire me to research something and to make a video about it, and Superkid is exactly one of those examples. When I heard talk of some of the crazy things that it did, I had to find out for myself exactly what it was doing. As always, thank you for watching.
Super